color for every pixel on the screen. So this entire main function is going to be run to color every single pixel. And so the setup here is that technically a fragment is not coloring every pixel in this grid, but we have a nice material that is the exact size of the screen, so that it happens that every fragment lines up with a pixel. And if you see at the bottom here, there's this number 2. This kind of gives you an idea of that. But by default, there's 2 pixels per fragment, so every fragment is like a 2 by 2 square. And it's hard to notice when we're starting, but if you start drawing like circles, and you have the pixel density at like 2, for example, it starts to look a little pixelated around the edges. So just something to be aware of. You might want to switch to 2.5. So, like I said, we're running this program to calculate the color of a single pixel, and that color is stored in this special variable called glFragColor. And it's a vector 4, which means it's a value that has 4 channels. And the first 3 channels we're setting to 0 for black, and then an alpha value of 1. So for example, if we change that to green, now every time this program is running, we're setting the pixel color to green. And put it back to black because I can't see the UI at the bottom. Down at the bottom here, there's this question mark button, which is extremely helpful. And if you click on that, you'll get the function reference, which is pretty much the built-in documentation. So now it's referring to green there. If we look in this list of the colors, we see green as this value here. And we can actually just like take that value and put it directly in, and it's the exact same thing. So here you can really clearly see that we have 4 values. We have the first 3 is 0, 0.71, 0.73, and then 1. And this also shows the bounds for these values. Those numbers are going from 0 to 1. So 1 is full on the red channel, and 0 is the bottom end of that channel. And so the other, it's really hard to see that one now. A really important thing to always keep in mind is the types of your variables. It's kind of like a cause of all of the errors is mismatched types. But another button that I'll show you is at the bottom here, this little picture of the bug. If you click on that, so you have it enabled, when you're making a mistake, you'll see a very helpful error message on the side there. And so whenever you have like mismatches like this, not enough provided for a constructor, because it's a vector 3, we need 3 values in there. And so all the vectors can be built up of smaller vectors, so you can make a vec4 with 2 vec2s, for example. So here we have, let's do this instead. Red and green are 0, and then blue and alpha are both 1. And so the last thing that I wanted to show while we're talking about colors is this concept called swizzling, where you can take out the components of a vector with either RGB, which would take out. We can take both of the reds. You can take red 3 times if you want. But however many letters you're having here is corresponding to the size of the vector in your output. And then, so we have RGBA, X, Y, Z, and W. You can use are the exact same. S, T, P, and Q is the other ones. And of course, you can use like this array indexing notation where you're taking out the first value from that vector. So what else? Can't see my mouse. Go back to the reference and we'll go over another tab. We have the uniforms here, and so because this is a program that's being run on every pixel for every frame, uniforms are these special values that don't change while you're shading in the whole screen. So for example, mouse N is going to be the mouse position at the beginning of rendering that frame, and so we can use in here, if we take mouse.x, we'll use the x coordinate of our mouse as how much red we want in the color. So now, like, as you're dragging your mouse around, we're feeding that value into the color. And so there's a couple of these variables that have n at the end. The difference between mouse and mouse n, mouse is going to be centered at the middle of the screen and go 0 to the right and positive to the right and negative to the left. Mouse n, 0, 0 is the bottom left corner, and 1, 1 is the top right corner. And so it's a good idea to try and keep values between 0 and 1, and then you don't really have to think about rescaling them all the time. And so the last two components, Z and W, are the last location of where you've clicked. So Z is the X location where you clicked. If we put it at full and we take out the other two, we get full blue. Okay, so let's look at some other. We'll come back to time and bands. Time is just an increasing clock, so you can start to get some motion into what you're drawing. And bands, if you have any audio coming in, it's a VEC4 with the low bands, mid-low, medium, and then high. Okay, so the add-on tabs is kind of like the nice, fun place to start, where you've got a whole list of functions to play around with and start drawing. We can use, let's look at UVN. So UVN is a VEC2. So you've got two values, X and Y. 0, 0 in the bottom left, 1, 1 in the top right. And it's the color of it's the position of the pixel that you're currently rendering. So here we can use it. We'll pass in the X value. So for these pixels, we've got an X value of 0 on the left. And as we go further to the right, we're increasing up to 1. And so then we're drawing with this, we're changing the color based on where you're at in the frame. So again, we're in a language very close to C. So we can have some variable declarations, and they look like the value of the variable, the type of the variable, the name of the variable, and then the equals the value on the right. And you have to make sure that, of course, the types are lining up. So here we're saying it's a VEC3, so we definitely need to multiply it. We have white, which is also a VEC3, and then we can scale that like UVX. And then we'll use our variable in the output here. So when you start building up with variables, we can change kind of the color that we're working with. And you start to build up these properties where you design like the scene that you want, and you have a few key ones that you want to react, like perhaps to the music or to the position, stuff like that.
So we also have a bunch of math functions we can use. So for example, we can take the sine of our x position here. And this is a value in radians, so let's do times pi 2 times s. Right, so here we're masking our green with a sine wave. And so this is our position within that, within the period. So if we're multiplying by pi 2, right, then we're going 0 to pi 2, which is one full sine wave. So we've got like 0 here, full power kind of in the middle, and then we go back down to 0. We're going negative and then back up. And so if we change here, now we've got 2 periods of a sine wave. Right, 3 periods. And start to build it up maybe in the other direction as well. Right, so you got this kind of like checkerboard effect. And here we can start using that, the uniform time. So, whoops. Right, this time is an ever increasing clock. So if we use this time, let's do mod pi. No, we can't. Slow it down a bit. And we still want maybe, I don't know, 50 checkerboard. And so this time is always increasing, so we're like working our way through the sine wave there. So another really useful function is the step function, which acts as our mask. So here we can multiply our color by step, and we'll say that anything to the right of 0.1 gets a value of 1. Everything to the left of it gets a value of 0. So when we're multiplying by that step, we're like creating this mask right on this border of at 0.1. So this is kind of how you start drawing shapes. Instead of building up these geometries, you want to define like how much into a shape a pixel is. So like if you're drawing a circle, you want to say, is our current pixel in the circle? Yes or no, and multiply your color by that mask. So the other one is smooth step. So we go 0.1 to 0.6. It's a little hard to see here. So here smooth step is kind of like the nicer version of step where it's not so sharp. Instead of cutting off immediately at 0.5, here we're saying that our cutoff is in between 0.5 and 0.6. And if you're anywhere in that gray area, just blend it. So then you get this softer edge rather than the really hard one from before. Maybe that was a really rigid line. We can also put mouse n in there maybe. So if we cross over that boundary, then we're getting the full strength of the color. So here, I was talking about a circle before. Oops. I don't want that to grow. Another nice, really convenient function to keep in your pocket. Distance, we're just going to compute the distance from 0.5, which is the center of our screen, to the current pixel. And then if we're using that step function, we're checking if that distance is less than 0.5, then we're going to fill in our circle. So then that second parameter effectively becomes like the radius. And so again, it's a very different way of thinking than drawing a circle. You're instead drawing, you're saying like how full power should this color be based on if it's inside or outside the bounds of the circle. I think we'll leave up an example with the time. I'm going to give you guys a chance to look at the functions, I guess, a bit more. And ask any questions. Actually, there's one more thing that can make a big difference, so I'll show it to you guys now. In the reference, if you kind of scroll down towards the bottom, there's a lot of these oscillators, which are like a really cheap way to get some motion into your shader. So these were taken from punctual, which we were looking at yesterday. So the sine, tri, saw, and square oscillators, and they take a frequency as a parameter. So instead of doing some math to calculate where you're at in the sine wave, you can use one of those oscillators. And put a frequency in there, and maybe a phase as well. Just get in. If you can see the difference as you're moving the mouse, you're like panning the phase. And then the third one is a time variable if you want. So we can actually use mouse in for that one. So like as you move left to right, instead of being based on time, how your position in the oscillator is based on where your mouse is. It's like as you move left to right, you're moving through the sine wave. I don't know if you guys can see that. And so all these sine oscillators go from 0 to 1 again, so they're really easy to plug into all these other functions. Maybe that's another one we can do. We can look at the tiles. I really like the tiles. So here in the function reference is kind of like this tile system, which makes doing those calculations for whether you're inside a shape or not a lot cleaner, and also implemented very efficiently, because when you start to draw this shape, if you're using a for loop, you can kind of hit a performance barrier pretty quickly. But with these tiles, effectively, you can check which tile you're working in and then build the shape from there. So here we want this 5 by 5 from the middle to the right and middle to the left. And then in each one we're drawing a circle tile with radius 0.1. It goes all the way up to 1. And this last value is the feathering. So as that increases, it gets blurrier. And with 0, this is where that pixel size comes in handy. So you can just like get that a lot crisper. And so these values intentionally go from 0 to 1, so like you can also plug in those oscillators right in there. And so they handle the negative numbers by just taking the absolute value of those, which is why when you go to 0 here, instead of going into negative and having a negative radius, it starts to build up again. So just look at some of the other tiles. The donut one. This regular polygon tile takes the number of sides you want as that second parameter there. So you can make some squares. And also we can rotate those. And you always need to pass in that tile as the first parameter. So here we're at a rotation where 0 is not rotated at all and 1 is the full rotation. And so we're back upright, and that means we can just plug in these oscillator values as well in there and get them rotating. And each of these tiles is a vec4, so we have the first two x and y, which is your location inside the tile. But then there's also z and w, which is the position of the tile with respect to the whole board. So like the tile in the middle would be tile 0, 0. And so to get these effects where maybe you want the outer ones to be rotating faster than the inner ones, we can multiply our frequency by tx. Oops, tz. So here are the ones on the edge that are, let's add 0.1 to that. So you can always see them. Nope. So this z is 0 for the middle ones, which is why they're not moving. And then as you go away from the middle, you get your tile coordinate that's changing the frequency of that oscillator that's controlling the rotation. And so because sometimes you don't want 0, 0 to actually be 0 because it breaks everything else that follows it. There's that width-centered chords. Takes our tile and then we can give it a new center. So let's say 1.0. So now the tile at the middle is actually 1, 1 and then increases from there as you go out so that we actually get some rotation on that middle one. And then we can you can kind of connect up those oscillators to all these different properties and start getting some motion in there. And then this is my new favorite function as of last night when I started using it. So here we're using our z coordinate, but we have too many of those, so let's divide by 15. And let's make it fully bright. Right, so now we're calculating our position on the color wheel based on which tile we're at, so we can feed that number in. We can also go within the tile, which goes from 0 to 1. So here we should get the full color wheel. to the green tiles and stop them from rotating and stop them from pulsing. So the other last thing I want to show you is how to start doing some animations, which are a little bit awkward because you don't have very much state between frames. So you can use this animate function, and we'll say we want the duration to be 2 seconds. And so what this does is it will create a vec3 where x and y are the start and end times of our 2-second frame, which is kind of how you can slow things down. And if you ever want to use random numbers, they're not completely random. They're completely based on whatever seed you provide. So you need to provide some number that won't change. Let's get this. So here, for just using like rand time, this is going to blink out of control. Or if you're using the animation, this number won't change for the entire duration of the 2 seconds. And so if we use our HSV again, we can pick our color based on the start of the frame. We can say a.z, which this number is how far we're along in our animation. So as we go from the beginning of the frame to the end of the frame, we'll get more colorful. So every 2 seconds, we fill in with whatever random color we pick. It gets brighter starting from white. I think the only other thing in this list is the lines. If you want to play around with those. I don't know, I think the best way to learn a language is to just play around with it. So yeah, I'll let you guys do that.